Welcome students. Now I am going to start the engineering dynamics course for this summer. Today in this lesson we are going to introduce the engineering dynamics, and then we are going to know the particle motion in a straight line, right? So first, what is mechanics? So this is the Hibbeler dynamics. So mechanics in this book is defined as a branch of physical science that is concerned with the state of rest or motion of bodies subjected to the action of force. So mechanics is the study of a body which is at rest or in motion, right? And if it is subjected to the action of forces, right? So in mechanics we both study rest and motion along with the action of forces. Then mechanics is further divided into statics, and then it is further divided into dynamics, right? So as we have learnt in the previous statics engineering statics course, that the engineering statics is concerned with the equilibrium of bodies, that is either at rest or moves with constant velocity, right? So in statics we deals with such objects which are in equilibrium, right? So equilibrium means that either the body will be in rest or either it will be moving with constant velocity. So when a body is moving with constant velocity, so then this means that there is no change in its velocity, and whenever there is no change in the body's velocity, so then there is no accelerations. So we can say that statics is the study of those bodies which are not accelerating, right, whose velocity is not changing. So whenever a body is in equilibrium, so its acceleration will not be changing, it will always remain the same. So we can write that statics is the study of bodies which are not accelerating, right? So not accelerating. And similarly, this course dynamics deals with those bodies which are accelerating, right? So which are not in equilibrium, right? So accelerated bodies. So here it is said that dynamics deals with the accelerated motion of body, right? And the subject of dynamic will be presented in two parts, right? So the dynamics is further divided into two parts, right? So if I write, if we classify the dynamics, so then it is divided into further two types, and one type is kinematics, right? So we can write it as kinematics, and the other one is kinetics, right? So kinematics deals with the motion of the body only, right? So this only deals with the motion, right? And kinetics deals with the forces of the body, right? So it is said that kinematic treats only the geometric aspects of the motion, right? So the kinematics only concerns with the geometric aspects of the motion, right? And there is no concern with the application of the applied force, right? So we only consider the motion, we do not consider the application of force. We do not bother about the force which is applied on that object, right? And in kinematics, it is the analysis of forces causing the motion, right? So in kinetics we deal with the application of the forces that are causing the motion, right? So this means that in kinematics we will deal with the Newton laws, that is the gravitational laws, etc. So in this book we will only deal with those objects. In this dynamics course we will only deal with objects with having the motion, right? And we will not consider the in the first part of this lecture we will only consider the particles motion, right? And then we will consider the kinetics portion at the end, right? So now we will learn what is rectilinear kinematics, right? So kinematics again. So now we will only deal with the motion, right? So kinematic means motion and rectilinear means linear, straight path. So straight path motion, right? And we can say that it is continuous motion, right? So it is said that we will begin our study of dynamics by discussing the kinematics of particle that moves along a rectilinear or straight line path, and recall that a particle has a mass but negligible size and shape, right. So in the initial studies of dynamics we will consider the particle motion, right. So what is particle? So particle has mass but negligible size and shape, right. So what is particle? So particle has mass, right, it has mass, right, and its shape and size are negligible, right. So shape and size are negligible. So it is said that therefore we must limit application to those objects that have dimensions that are of no consequence in the analysis of motion, right. So we will consider all those objects which have dimensions, but those dimensions will have no effect on the analysis of motion, right. So we can say that we will assume that the dimensions of this object has no effect on the motion. Let's say if we consider a car, right, so its shape has effect on the motion, right. So it is producing the drag or friction force, but in the dynamics, in the study of particles, we will assume that there is no effect of that dimension of a car on its motion, right. So in most problems we will be interested in the bodies of finite size, right. So we will be interested in bodies of finite size. So what is meant by finite size? So finite size means that we will consider those bodies which have some boundaries, right. So whose boundaries are visible to us, right. So for example, if we consider rockets, projectiles or vehicles, so their boundaries are visible, right. So those objects have finite sizes, right. So we can say that a car could be considered as a finite size, right. So we will consider the finite size bodies in this dynamics, and it is said that each of these objects can be considered as a particle, right, as long as the motion is characterized by the motion of its mass center and any rotation of the body is neglected, right. So in the dynamics we will consider all those objects whose motion is studied due to its mass center, right. Or we can say that, let's say if we have a car and if we are studying the motion of its center of mass or its center of gravity, right, so then that could be considered as a particle, right. And the next assumption will be in dynamics that there is no rotation, right. So the particle has a mass and its shape and size are negligible, right, and we can say that finite mass or size, or we can say that finite size right. So car could be considered as finite size as its boundaries are visible, right. We can consider it as a mass with boundaries, right, or we can consider it as an object which has some boundaries, whose boundaries are visible to us. And similarly, if we are considering the motion of the center of mass of a body, so then that could be considered as a particle motion, right. And the next assumption in dynamics will be that there is no rotation of a body, or we can say that the rotation of a body is neglected. So in rectilinear kinematics, the particle motion is characterized by, we can say that its motion is specified by some parameters, right, and those parameters are its position, right. So the position, the velocity and acceleration, right. So we already know the definition of position, velocity and acceleration, but I will explain them shortly, right. So when a body is moving in a straight line, so let's say that this sphere is a particle which is moving in a straight line, right, and we can say that this is the direction of motion, right, or we can say that this is the positive position, right. So let's say that this is the particle and this O is the origin, right. So if we draw if you want to represent the position of this object, so we can draw an arrow like this, right? And we can say that this is the position vector of this object, right? And if let's say that this is the origin, and let's say that this distance is let's say 8 meters, right? So then we say that the magnitude of this S is 8 meters. This means that this object is at a distance of 8 meters from its initial position. Let's say that this is its initial position, right? So it is the position of the body, right? So the straight line path of a particle will be defined using a single coordinate axis, right? So this means that we can specify the position of the body by a single coordinate system, right? So we only need single coordinates, right, if a body is moving in a straight line. And the origin O on the path is fixed point, right? So this origin O is fixed point, and from this point the position coordinate S is used to specify the location of the particle at any given instant, right? So let's say if this is the initial position, right, and this particle is moving on this straight line, so we can specify the position of this object considering this as the initial, this O as the initial position of this particle, right? And let's say that this side, this is positive S. When the body is moving towards right, so the position could be considered as the positive, right? So as we can see that we have drawn this arrow, right? So this means that position is a vector quantity, right? So it has a magnitude and it has a direction, right? So if this particle was moving towards left, if this body was located somewhere here, right, so then its position could be represented by this arrow, right, and this is the origin. So then we would say that, let's say that this is minus S, right? So then this position magnitude is negative and it's in the opposite direction, right? This means that this is the vector representation of this position, right? So the position is a vector quantity, right, since it has both magnitude and direction. And now how to define the displacement? So we can say that displacement is the displacement of the particle is defined as the change in its position, right? So whenever there is a change in its position of the particle, right, so then we say that the particle has traveled some displacement, right? So the change in its position, so we can write that the displacement S is the final position minus the initial position, right? So the rate of change of position, we can say that the change in the position of a particle is known as displacement, right? So let's say that this is the particle and this particle is initially at some distance S, right? So this is the initial position, right? And then after some time this particle has reached this position, right? So if you want to find the displacement, so then displacement will be the final position. So the final position from the origin is the magnitude of that final position is, let's say, S dash meters, right? So we will write S dash and minus the initial is this, right? So the displacement of the particle is defined as the change in its position, right? So the change in the position of the particle is known as the displacement. And for example, if the particle moves from one point to another, the displacement is this, right? So the final position minus initial position. So now in this case the delta S is positive since the particle's final position is to the right of its initial position, right? Since we are considering that towards the right the particle motion is positive, this is positive S, right? So this means that S dash, if the particle is in such position, right, so if this is the initial position and this is the final position, so then this means that S dash is greater than S, right? So this means that this delta S is positive, right? So if S dash is greater than S, so then this difference will be positive, right? So this means that the displacement is positive. Similarly, if initially the particle was here, right, if we consider that the initial position of the particle is somewhere here, this is the initial position. Let me write that this is the initial position of this particle and this is the final position, right? So if then we find the delta S, so then the final position is this. So the final position as S and the initial position is S dash, and now the S is less than S dash, right? So this means that, let's say, if this S dash is 8 meters and this S is, let's say, 5 meters, so then this difference will be negative, right? So if I write, so then S is 5 and then the initial position is 8 meters, so then this is minus 3 meters, right? So in this case the displacement is negative, right? So when the final position is less than the initial position, so then in that case the displacement will be negative, right? And if the final position is greater than the initial position, so then in that case the displacement will be positive, right? So this means that the displacement is a vector quantity, right? So delta S is positive since the particle's final position is to the right of its initial position, and likewise if the final position were to the left of the initial position, right? So in the second case the final position of the particle is towards the left, and in the initial case the final position was towards the right, right? So if the final position is towards the positive S, so then the displacement will be positive, and if the final position is towards the negative S, right? So this is the final position, right? Or this is towards positive, right? And in the second case this is towards the negative, right? So if the particle is moving towards the negative coordinates, right? So this is our positive coordinate and this is our negative. So if the final position is towards the negative, so then this means that the displacement would be negative, right? So the direction of the displacement will be from the initial position of the particle towards the final position. So in the initial case the displacement vector will be this one, right? So we can consider this vector, right? So this will be from the initial position towards the final, and in the second case this will be the representation of the displacement, right? So in the first case this direction is the representation of positive displacement. This is delta S vector, right? And this is positive, right? And in the second case this is the vector representation of the displacement, right? So displacement is a vector quantity, and it is said that it should be distinguished from the distance the particle travels, right? So if this was the initial position, let's say if this was the initial position, this one, if this is the initial position and this is the final position, right? So if we want to find the distance traveled by this particle, so in this case the distance traveled will be always positive, right? So if we write that distance traveled will be the final position minus initial position, but we will always represent that as a positive value, right? So we will differentiate, we will distinguish displacement from the position of the particle or the distance traveled, right? So it is said that it should be distinguished from the distance the particle travels. Specifically the distance traveled is a positive scalar, right? So distance traveled is always a positive scalar quantity, right? So distance traveled is scalar quantity, right? So if someone says that what is the distance traveled by this particle, right? And if this is the initial condition, if the initial distance is the initial position of this particle from the origin is 5 meters and the final position of this particle from the origin is 8 meters, so the distance traveled will be 8 minus 3. So we will always say that the distance traveled is positive 3 meters, right? And there will be no vector representation in that case, right? So the distance traveled is always positive scalar, while the displacement could be negative, could be positive. So it's a vector quantity, and that displacement could be represented by an arrow, right? By a vector. Now we will define the velocity. So if the particle moves through a displacement s during the time interval delta t, so the average velocity of the particle during this time interval is delta s divided by delta t. So if the particle has traveled some displacement, if the particle has moved from the initial position to somewhere this point, so then we say that this particle has traveled through some displacement and some time interval, right? So this particle will take some time. Let's say that this particle take let's say 3 seconds from this position to this position, so then we will say that the average velocity of this particle is delta s by delta t. So, and then if we take smaller and smaller values of t, if we consider the motion of this particle in very small intervals, let's say that if initially this particle was somewhere here and then after very small interval this particle is somewhere here, right. So, if we decrease or if we divide the interval in very small subparts, so then in that case the velocity could be considered as instantaneous velocity, right. So, if we consider very small delta t, if this delta t is very small, right. So, then in that case the average velocity can be converted into instantaneous velocity. So, then in that very small interval of time we can say that this is the instantaneous velocity at that particular instant, that will be the velocity of that particle, right. So, this is the instantaneous velocity. So, then if we take if this is v delta s divided by delta t, and if we take the limit and if delta t tends to 0, right. So, if this delta t is very close to 0, so then that velocity will be instantaneous velocity. So, this will be instantaneous velocity. And as we can see that as delta t can never be negative, right. So, delta t, the time interval will always be positive, right. So, then we can say that if this delta t is always positive, right, if this is always positive, so then delta s, the displacement could be positive and it could be negative, right. So, this means that the direction of the velocity will be the direction of the displacement, right. So, the sign used to define the sense of the velocity is the same as that of delta s or ds, right. So, this means that if delta s, if the change in the position is positive, right. So, if the displacement is positive, so then the velocity will be positive, and if the displacement is negative, so then the velocity will be negative, right. So, let us say that this is the initial position and this is the final position, right. So, this is the initial position. So, let us say that this is s and this is the final position. So, the final position value is greater than the initial position. So, then this means that delta s is positive, and if delta s is positive, so then the velocity is positive, right. So, this means that if this is the initial position and this is the final position, so then this is the vector representation of delta s, right, and then the velocity direction will be the same as that of the displacement, right. So, if the displacement is positive, the velocity will be positive, and if the displacement is negative, so then the velocity will be negative. And the magnitude of the velocity is known as speed, right. So, we know this. So, the magnitude of the velocity will always be known as speed, right, and the speed is a scalar quantity, right. So, it has only magnitude and it has no direction. So, it is said that sometime we use the average speed. So, what is average speed? So, average speed, let us say if I write, so average speed is total distance traveled divided by total time taken, right. So, what is meant by the average speed? So, let's say that this is the initial position and this is the final position, right, and this particle has traveled some distance in this direction and then it traveled back, right. So, the total distance will be from this point to this point, right. So, and the displacement will be from this initial position to this final position, right. So, this will be this delta s will be the displacement and the total distance travel will be this path, right. So, let us say that this particle has moved until this point and then it traveled back to this point. So, the total distance will be this distance plus this distance. So, this will be the total displacement, right. So, for example, it says that the particle in figure 12.1 d, right. So, this is 12.1 d travels along the path of length st, right. So, this is the path of this particle. Initially, this particle moves toward right and then it travels towards left. So, this is the path of this particle, right. And this total distance, this distance traveled took some time interval, and that time interval is, let's say, delta t. So its average speed will be st, total distance traveled divided by total time. So let's say that initially this particle has traveled some distance, let's say this is s1, and then this particle was somewhere here, this is, let's say, s2, right? So the initial position is s2, and then it traveled to some distance at s3, let's say this is s3, let's say, and then initially the particle was at a distance of s2 from the origin, and then it traveled to s3, and then it returned back, and then it reached to this position, that is the s1, right? So the total distance will be as this is the final position and this is the initial, right? So this delta s, let's say that I write that this is delta s1 and then this will be delta s2. So the total distance will be delta s1 plus delta s2. Delta s2, right? So the delta s1, so this is the delta s1, let's say. So this will be s3 minus s1, and remember that this is the total distance. So how we will find the total distance? So I have already told you people that the distance will always be positive, right? So this will be s3 minus s1, right, plus this distance, this delta s2. So this is the final position in this interval, right? So in this interval, this is the final position, this is the initial position. So the initial position is s3, right? So I will write s3 minus s2, right? So now let's say that, let me clear this. Let's say that initially the particle was somewhere here, let's say, and the initial position from the origin was, let's say, 3 meters, right? And then this particle traveled to this point, and let's say that this distance is, let's say, 7 meters, and then it turned back, right? Then it turned back, and then it reached to this point, let's say. This is the final position, right? So initially the particle was here, then it traveled to this position, and then it traveled back to this position, right? So this is the initial position. Let's say that I write that this is the initial, this is s1, and this is the final position, right? So now if you want to find the total distance traveled by this particle, so total distance will be equal to this distance plus this distance. So this particle has traveled initially from this position to this position, and then it traveled back to this position, right? So the total distance will be, let's say this is delta s1, and let's say this is delta s2 plus delta s2, right? And we are finding the total distance, right? So the distance will always be positive. So now delta s1 will be, this is distance, so we will take the absolute value. So delta s1 will be the final position, so this is s1 minus the initial position, right? And the s1, the particle was at a distance of 7 meters, right? So we can write that this is 7 minus the initial position is 3 meters, right? So we will write 3. So delta s1 is 5 meters, right? And let's say that delta s2, right? So then the final position in this case, in this interval, right? So this will be sf minus s1, and we will take the absolute value, right? So then the final position is, let's say that this distance is, let's say, 1 meters. So then 1 meter minus, and this s1 is 7 meters, and we will take the absolute value whenever we are finding the distance, right? So this is minus 6, and we will take the absolute value, so this is 6 meters. So the total distance covered by this particle is 5 meters plus 6 meters, so this is 11 meters, right? So if we look again, so then initially this particle traveled from this point to this point, so then this distance is 5 meters, right? From here to here it traveled 5 meters, and then from here to here it traveled how much? So it traveled 6 meters. So the total distance traveled by this particle is 5 plus 6, so this is 11 meters. And if we are asked to find the displacement, right, so the displacement, the total displacement will be the initial position, the final position minus the initial position. So the final position is 1 meters, right, so 1, and the initial position is 3, right. So this is minus 2 meters. So this means that the direction of the displacement is from this point to this point, right. So this is the vector representation of that displacement. This is delta S, this is displacement, right. And the distance traveled is 11 meters, right. So the velocity from this point to this point, the average velocity in that case will be delta S divided by total time taken, right. So delta S in this case is, let's say this delta S is minus 2 meters, so we will write minus 2, and let's say it took 6 seconds, right. So this will be minus 2, so this will be minus 1 divided by 3 meter per second, right. So you people should know the difference between the total distance traveled and the displacement, right. So this is average velocity magnitude, and if you want to find the average speed, so the average speed will be total distance divided by total time taken, right. So the total distance in this case is 11 meters, right. So 11 divided by 3 seconds, the total time taken is, let's say, 3 seconds, right. So 11 by 3 is the average speed, and minus 1 by 3 is the average velocity. So the average speed is always positive scalar, and it is defined as the total distance traveled by the particle divided by the elapsed time, right. So this is the average speed, and it will always be positive since the total distance traveled is always positive, right, and the time is always positive. Now we will define acceleration. So if we know the velocity of the particle at 2 points, right, so then the average velocity will be the rate of change of velocity, right. So if there is a change in the velocity of particle, so then we will say that this particle is accelerating, right. So let's say that initially the particle was somewhere here, let's say, and let's say that this particle was at a distance of s1, right, from this origin, and let's say that this is s2 and this is s3, right, and s3 is greater than s1 and greater than s2 and greater than s1, right. So if there is a change in the velocity of this particle, so then this will mean that this particle is accelerating, right. So let's say that initially when the particle was traveling from s1 to s2 position, it took let's say 2 seconds, and let's say that s1 is 3 meters, and let's say s2 is 4 meters, and let's say s3 is 6 meters, right. So for this time interval, let's say that it took 2 seconds, and then it took how much? So let's say that it took 3 seconds from this point to this point, right. So if you want to find the velocity of this particle from s1 to s2, so what will be the velocity? Let's say that during this interval the velocity is v, right. So then v will be delta s1 divided by delta t, right. So let's say that from this point to this point this is delta s1, and from this point to this point let's say that this is delta s2. So delta s1 in the will be s2 minus s1 divided by delta t. So s2 is 4 meters minus 3 meters divided by delta t. So let's say it took 2 seconds, so this will be 1 by 2 meter per second, right. So this is v, and then let's say from this point to this point what is the velocity? So let's say that is v dash. So v dash will be s3 minus s1 s2 divided by delta t, right, and let's say this is delta s2, right. So s3 is 6 meters, the particle has reached a position of 6 meters, s3 is 6 meter and s2 is 4, right. So 6 minus 4, and let's say it took 3 seconds, so this is 2 divided by 3. So v is not equal to v dash, right. So this means that there is a change in the velocity, right? So initially the particle was moving with this velocity, and after some time interval, in the second time interval, it was traveling with this velocity. So there is a change in the velocity. So whenever there is a change in the velocity, so this means that this particle is accelerating, right? And if the change in the velocity is positive, so this means that the acceleration is positive. And if the change in the velocity is negative, so then this means that the acceleration is negative, right? So now we can say that the velocity at this point is 1 by 2 in our case, right? And the v dash is 2 divided by 3. So at this point the velocity is 1 by 2, and at this point the velocity is 2 by 3. So what is the change in the velocity, right? So the change in the velocity will be the final velocity minus initial velocity. So the final velocity is v dash and the initial velocity is v, right? So this is the final velocity is 2 divided by 3 minus 1 divided by 2. So what is this difference? So this is the LCM is 6. This is 4 minus 3. So this is 1 by 6. So this is the change in the velocity, 1 by 6 meter per second. And let's say that at this particular point the velocity is 1 by 2, and at this particular point the velocity is 2 by 3. So how much time it took to change from this velocity to this velocity? So the change in the interval is 3 seconds, right? So let's say that from this velocity, from 1 by 2 meter per second to 2 by 3 meter per second, the particle took, let's say, 3 seconds. So the acceleration will be change in velocity divided by change in time interval, right? So this will be 1 divided by 6 divided by 3 seconds, right? So this is 1 divided by 18 meter per second square, right? So this is the acceleration. So again the average acceleration will be the total change in velocity divided by total time, and if we decrease this time interval, if we consider the time interval very close to 0, so then in that case we can say that acceleration is instantaneous acceleration, right? So instantaneous acceleration will be dv by dt, right? And this is delta v by delta t. So if we apply limits, so then in that case the acceleration is dv by dt, right? And if we write, so acceleration is dv by dt, the rate of change of velocity, right? So again, if this is the case, if this is the particle and this is the particle, let's say at this point the velocity is v1 and at this point the velocity is v2. So if there is a change in the velocity, so then there will be acceleration, and if the final velocity is greater than initial velocity, so the change in velocity will be vf minus v1, right? So if final velocity is greater than the initial velocity, so then change in velocity will be positive and the acceleration will be positive. And if the final velocity is less than the initial velocity, so then the change in velocity will be negative, right? This difference will be negative, right? And so in that case the particle will be deaccelerating, the particle will deaccelerate, right? So eventually if the velocity is decreasing, so eventually the particle will stop somewhere, right? After some time interval. So if acceleration is dv by dt and if velocity is ds by dt, right? So we can write it like this as well. So this way d by dt, and velocity is itself ds by dt, right? So this means that we can write acceleration in terms of the displacement as well. So this will be d square s by dt square, right? So we can represent acceleration in terms of position like this. So acceleration is dv by dt and acceleration is d square s by dt square, right? So if we take double derivative of the position, right, so then we will be able to find the acceleration, right? So this a is d square s by dt square and acceleration is dv by dt. And if change in velocity is 0, right, if this is the case, if the change in velocity is 0, so then acceleration is, let's say, del v by del t, and if this change is 0, so then the acceleration will be 0, right? And at that particular case the acceleration will be 0, right? And the particle will be moving with the uniform velocity. So whenever the particle is moving with uniform velocity, so then we can say that the acceleration of that particle is 0. Now we can define one another relation between the acceleration, position and velocity, right? So this is the relation between acceleration, position and velocity, right? So first we have defined velocity, which is ds by dt, and then acceleration is dv by dt, right? And now if I write dt from this equation, from this formula, so then dt will be ds by dv, right? And if we write dt from this equation, so then dt will be dv by da, right? So if we equate both of these, so then ds by v will be equal to dv by a, and if we cross multiply, so then a ds will be equal to v dv, right? So this is this third equation, this is 12.3, right? So it is said that although we have now produced three important kinematic equations, this is first equation, this is second equation, and this is third equation, but it is said that the third equation is not independent of these two equations, right? So this third equation is dependent on these two equations, right? Remember, as we have derived this third equation from these two equations. Now as we have derived three equations, right? So one is the acceleration equation, let's say. So acceleration is dv by dt and velocity is ds by dt, right? And a ds is equal to v dv, right? So now if we consider the case when the particle is moving with constant acceleration, right? So if the acceleration is constant, so then we will put a is equal to a constant, right? So this is, let's say, a constant, right? So the acceleration is not changing, let's say. So if the acceleration is not changing, so then we will use that constant acceleration, and then we will find the velocity and the position by integrating these differential equations, right? So this is, if you want to find the velocity, so then this will be dv is equal to ac dt, and if we want to find the velocity at after some time interval, so then we will integrate that, right? So we will learn these in the example when we are given some data, right? So if we want to find the velocity as a function of time, right, and if the acceleration is constant, right, so this is ac is dv by dt, so this is the given equation and the acceleration is constant, right? So this will have some constant value, let's say that acceleration is 3 meter per second square, right? So if the acceleration is not changing, so it will have some constant value. If the acceleration is changing, so then we will have the acceleration equation, right, with respect to time. So if the acceleration is not changing and we are asked to find the velocity equation, right, so then what we will do is that we will write this dv and we will multiply this dt with this ac, so then we will have ac dt, and then we will integrate. And let's say if it is said in the given problem that at time t equals to 0, the velocity, the initial velocity is v naught, let's say, and let's say the final velocity is v and the final time is t, right? So then we will integrate. So now when we integrate this, so then this is only dv, so then this will cancel out, so then this will be v from v naught to v, and this will be ac from ac, and when we integrate this is constant, right? So this will come out of the integration, so then this will be act, and this will be from 0 to t, right? So then when we apply these boundary conditions, so then this will be v minus v naught, and this will be act minus ac into 0, right? So this will be v minus v naught act. And if you want to find the final velocity, so then this final velocity will be equal to v naught plus act, right? So this equation is applicable only when the acceleration is constant, right? So again, as we can see that this is the first equation of motion, this is first equation of motion, right? Now if you want to find the position as a function of time, so then we will use this equation, so then ds will be equal to v dt, right? And then we will integrate, right? So we can integrate this, and let's say that at time equals to 0, the initial position is s naught, and and the final position is s, let's say, and we are integrating this with respect to time. So then we will put the initial value of t. So the initial value of t is 0, and after some interval the time will be equal to t, right? So then and this velocity, if the acceleration is constant, so then the velocity as a function of time is given by this equation, right? So just we have derived. So then what we will do, we will put this equation in this integration, right? So then this velocity is a function of time and the acceleration is constant, so this is given by this, right? So then ds from s0 to s, and this is from 0 to t, v0 plus act, and when we integrate this, so now if I write that this is ds from s0 to s, and this is v0 plus act dt, and this is from 0 to t. So when we integrate this, so then this will be s from s0 to s, and this will be, when we apply the integration, so then this will be v0 dt from 0 to t plus ac is constant, so we will write ac, and this will be t dt, and this will be from 0 to t, right? So now if I integrate this, so then this will become s minus s0, and then this integration, so this will be v0 t, so this will be v0 t, and this will be plus ac, and this t dt, so the integration of this is t square divided by 2, right? So s minus s0, so this will be s, the final position will be equal to s equals to s0 plus v0 t plus ac t square divided by 2. So again, as we can see, this is the second equation of motion, right? So s is equal to s0 plus v0 t plus ac t square by 2, and this equation is only applicable when the acceleration is constant. Again and again, these equations are for constant acceleration. So now if you want to find the velocity as a function of position, so then we will use this third equation that just we have derived. So v dv equals to ac ds, and let's say that at initial position we are integrating this with respect to s. So at the initial position, the initial velocity is, let's say, v0, and after some time interval, after some distance, after traveling some distance, the final position is s, so then the final velocity is v, let's say. So now if we integrate this, so then this is v dv, so then this will be v square divided by 2, and this will be from v0 to v, and this acceleration is constant, and then this ds, so when we integrate this, so then this will be acs from s0 to s, right? And let's say if we apply these boundary conditions, this is v0 and v, so then this will be v square by 2 minus v0 square by 2 equals to ac, and this will be s minus s0, right? And if we take 1 by 2 common from this, so then this will be 1 by 2, this will be v square minus v0 square is ac s minus s0, and if I multiply this 2 on the other side, so then this will be 2 multiplied, and if we want to have the equation for only the velocity, right, the final velocity, so then v square will be equal to v0 square plus 2ac s minus s0, right? So we are having this third equation of motion. So this is the third equation of motion, third equation of motion, right? So now we have the velocity in terms of position, right? So this is the velocity in terms of position. We can write that this is the velocity function in terms of position. Again and again I am telling you people that all these three equations that just I have derived is only when the acceleration is constant, remember, right? So when the acceleration is constant, right, when t is equal to 0, s is equal to s0 and v is equal to v0, right? So these are the conditions, right? So when initially when the particle is at some distance s0 and when initially the particle has some velocity v0, so then these three equations are valid, right? And the typical example of constant accelerated motion occurs when a body falls freely, right? So whenever the particle or a body falls freely, so then we can apply these three equations, because in that position, in that condition, when the body is falling freely, so the particle is moving with downward acceleration, and that downward acceleration is constant, right? So then for that particular case, we can use these three equations that we have just derived.